Hello, my name is Ankur Moitra. Today I'll be talking about learning with Massart noise and connections to fairness. This is based on joint work with Sitan Chen, Freddie Kohler, and Morris Yao. So in this talk, I'll give you provably robust algorithms for some basic problems in supervised learning. So let me start off by giving you a primer on supervised learning. The usual framework in which we study these kinds of problems is what's called the PAC learning model. In this model, we're given samples x, y, where x is a data point and y is a label that's either +1 or -1. And furthermore, we assume that y is equal to h of x for some unknown hypothesis h that lives in a known class. So for example, this could be the class of all half spaces, where we label everything above the half space as +1 and everything below the half space as -1. Now the goal here is to estimate h approximately. In fact, we want to probably get h approximately correct, and that's why it's called the PAC learning model. So in this talk, I'll be particularly interested in settings where there's noise. So what happens if there's no simple hypothesis that fits the data exactly? In fact, there are a few standard frameworks for talking about noise. Each one of them has their own strengths and weaknesses. One of the first things you could think of is what's called the random classification noise model, where you flip each label independently with some fixed probability. And indeed, in the RCN model, there are polynomial time algorithms for doing things like learning half spaces. Now, there are other settings in which making strong assumptions about the distribution of the noise isn't appropriate. And in those settings, you might be interested in the agnostic noise model, where you make no assumption about the structure of the noise, but you want to find the hypothesis that approximately best agrees with the labels you're given. The trouble is that in general, agnostic learning is computationally hard unless you make strong distributional assumptions. So for example, you could assume that x is log concave. And indeed, Danieli showed that distribution-independent agnostically learning half spaces is hard. In this talk, I'll be interested in intermediate models for noise that sit in between random and agnostic. So are there challenging noise models where we can still learn in a way that doesn't make any distributional assumptions on x? So in particular, I'll be interested in the Massart noise model, where the label of each point is flipped independently with some probability eta of x, but this probability eta of x can vary from point to point. Now there are a few interpretations of the Massart noise model. You could think about it as flipping each label independently with probability eta, but then allowing an adversary to unflip it, to choose to add less noise if he so chooses. Or you can think about an adversary as having arbitrary control over some fraction of the data, but the catch is that it's a random eta fraction of the data. Now these interpretations aren't exactly equivalent to the Massart noise model, but all of the algorithms that I'll talk about will work in them too, so I won't distinguish between them. Now the main question I'll be interested in is, are there distribution-independent algorithms for learning under these kinds of noise models? Recently, Diakonikoulis et al. Gave a polynomial time algorithm for improperly learning half spaces under Massart noise, and it achieves error eta plus epsilon. Now their algorithm is improper in the sense that instead of outputting a single half space, it outputs a partition of the domain into a polynomial number of regions, and along each one of the regions, there's a different half space you use to label the data. Now this has some problems because it's not easy to interpret the output of this algorithm because it's no longer a simple hypothesis. And there are many natural questions about their work. So for example, could we give proper learning algorithms? Also, their algorithm gets error eta plus epsilon, but that's actually not the best that you could hope for. So can you achieve optimal agreement within the class efficiently? So now let me tell you about our main results. First, we give a polynomial time algorithm for properly learning half spaces under Massart noise. It achieves the same error eta plus epsilon. It also has another number of appealing advantages, like improving the dependence on epsilon. Now, in fact, Diakonikoulis et al. Show a no-go theorem that there's no approach based on minimizing a convex surrogate that's going to lead to a proper learning algorithm. So how exactly do we get around their no-go theorem? Well, we design a general framework for tolerating varying noise rates that's based on a two-player zero-sum game. I'll tell you more about that in a few minutes. In fact, this general framework leads to new algorithms for learning richer families of hypotheses under Massart noise, like generalized linear models, which contain, as a special case, important things like logistic regression. Now, we also show a surprising connection between learning with Massart noise and the notion of evolvability. In particular, this connection allows us to prove lower bounds for learning under Massart noise, and we show lower bounds for statistical query algorithms that they need to make a super polynomial number of queries to get down to agreement opt plus epsilon. In fact, we also use a converse of this connection to give new algorithms in evolvability. So now let me briefly tell you about our general framework, which we use to design our algorithms. They're all based on the following two-player zero-sum game, where one player chooses a direction W, and another player chooses a way to reweight the distribution. And our goal is to measure the expected loss under this new distribution, under a surrogate loss, in our case, the leaky ReLU, which is given as follows. So it's related to the ReLU, but varies in some important ways. And here C ranges over all distributions over the domain. Now, it turns out that it's not hard to show that the optimal solution for this zero-sum game is the min player would play the true direction W star. So this tells us that if we could find approximately optimal solutions, we'd be done. Unfortunately, it's not easy to find approximately optimal solutions of this game directly. In fact, optimizing over the max player strategies is both statistically and computationally hard. So instead, we work with a relaxation where we restrict the family of strategies for the max player, and he's only allowed to reweight the distribution along slabs along the current direction W. Now, the intuition for this relaxation borrows a lot of ideas from Diakonikoulis et al., who show that instead what you can do with a surrogate loss is the W that minimizes it gives you some direction where you can pull off part of the distribution and find a hypothesis that's good on that portion of the distribution. Now, what they do then is recurse on the rest of the distribution where they haven't found a good hypothesis yet. Now, in contrast, we do the opposite. We use this direction W and the slab as a way to force us to improve the current estimate W via online gradient descent. Now, let me briefly tell you about some experiments in the context of fairness that get to the issue about when this noise model is useful. So we study the UCI adult data set, where there are about 50K individuals with 14 attributes each, and the goal is to predict whether the income level is above or below 50K. And we do something a little bit strange, which is we add noise outside the target group. Now, the motivation for this is that there are a lot of empirical studies that show how the level of noise varies across different demographic groups. And what we do is we measure the overall accuracy and the accuracy on the part of the target group that actually is above 50K. And we show some surprising things that a lot of off-the-shelf algorithms do catastrophically bad on the target group. And this is true for many different target groups. And what's going on is that when the noise rate varies across the distribution, many natural algorithms amplify biases that are present in data, whereas our algorithm does much better, presumably because it can tolerate heterogeneous noise. So I'll stop there. Thanks for your attention.
Hi all, hopefully everybody's staying safe and healthy. I'm Maggie and I am here presenting work that I've done with Lauren West, David Hooper, and Erica Shenoy from Massachusetts General Hospital, and Eric Horvitz from Microsoft, and John Gattag from MIT. In this work, we ask a question that I'm sure many of us have entertained over the last couple months. That is, can we build reliable infection prediction models for contagious diseases? Specifically, we're asking about models that make predictions for individuals, taking into account the evolving infection state over time. If we're able to answer this question in the affirmative, we can identify individuals who are likely to become infected and preemptively isolate them, hence slowing down the spread of the infection. Now, the challenges of building such models are many, but in this work we will focus on one particular problem, that is the problem of asymptomatic carriers. These asymptomatic carriers, which we've been hearing a lot about in the context of COVID-19, are individuals who are carrying a particular infectious disease, but they do not display the symptoms, so they don't get tested. In other words, they are infected but untested individuals. And the reality is this problem is not new at all. It is a problem that's been ubiquitous to infectious diseases. For example, the first asymptomatic carrier of typhoid fever was identified in 1930, and in our current day, there are other infectious diseases that are characterized by asymptomatic carriers that have riddled the healthcare system over long periods of time. One such example is Clostridium difficile, which is an infection that attacks the gut and causes about 250,000 infections every year, 14,000 deaths, and over $1 billion of excess medical costs. Now, in order to be able to build these reliable models, we need our model to pick up both symptomatic individuals. These are individuals who, when infected, become symptomatic and are likely to get tested, as well as asymptomatic individuals who might be infected but never get tested because they don't show the symptoms. And this highlights that at the core of it, the issue of asymptomatic carriers is really an issue of incomplete testing. If we test everybody, asymptomatic carriers will be identified and they will no longer be an issue. Now, by incomplete testing, I really mean that it's limited, meaning a small proportion of the population gets tested because of the limited availability of tests. And it's also biased because symptomatic individuals are far more likely to get tested than asymptomatic individuals. So a refined version of our previous question is, can we build reliable infection prediction models even if testing is incomplete? So let's think of what we need in order to answer this kind of question. First, we need individual characteristics that tell us something about the patient's susceptibility, such as like age or whether or not the individual is immunocompromised. Here we'll use X with an overline and a superscript T to denote an individual I's characteristic at time T. And in this work, we will assume that we have access to these characteristics. We also assume that we have access to the individual's contact networks, and here we'll use red to show that the individual is infected and blue to show that he is healthy, and gray to show that we still don't know. If we have all the neighbor's infection states, we can compute the individual's exposure at time t as the sum of his neighbor's infection states at the previous time points. And the final input to our model will be the concatenation between the individual characteristics and his exposure states. And what we want is to learn some function that takes us from this concatenated input to a label that is 1 if the individual is infected, whether or not they become symptomatic, and 0 otherwise. Now, in the setting I just described, we can minimize the weighted logistic loss, where we weight each individual I by 1 over his probability of getting tested, and this allows us to give a higher weight for individuals who are unlikely to get tested. But one thing that I've kind of swept under the rug is that we do not expect to know all the individual's neighbor's infection states. So instead, we will model the individual exposure as a latent variable that is sampled from some distribution Q. Q tells us the main individual's exposure state, and this will solve the problem of partially observed exposure states. We'll let this partially observed exposure state concatenated with the individual characteristics be denoted by this X hat. And now we can rewrite our original problem to say we want both F and Q that minimize this loss. But this Q not only allows us to know the individual's exposure states, it gives us a little bit more information. By imputing the exposure state, it is implicitly giving us a label for the neighbor's unobserved infection state. So now we have an imputed label for each neighbor that is imputed based on the main individual's infection state. So for a given untested individual, each one of their neighbor will have a vote on their own infection state. And we can think of this mean vote as a pseudo-label or a soft label that we can use to learn a mapping from the neighbor's characteristics to their imputed infection state if it is unobserved. And this gives us our final objective, where we iterate between finding the best Q and the best F, using both tested, meaning labeled, and untested, meaning unlabeled, data. For the latter, we will use the imputed label, which is imputed according to Q, and lambda here is a trade-off parameter, which is picked through cross-validation. We will use recurrent neural networks to model this function F. Now let's look at some of our results. In order to test the performance of our model, we simulate a universe where there are three types of people. The first is symptomatic if they are infected. These are individuals who are very likely to become infected if they are exposed, and they become symptomatic when they are infected, so they are more likely to be tested. The second group is asymptomatic if infected. These are individuals who are very likely to become infected if they are exposed, but they are asymptomatic, so they are unlikely to be tested. And the final group is the immune group. These are patients who are very unlikely to be infected even if they are exposed. And to simulate the three groups, we use the MNIST dataset. For symptomatic individuals, we use the pixels from the images with label 0. For asymptomatic, we use pixels from images with label 1. And for the immune patients, we use pixels from images with label 2. And we draw the contact network from a stochastic block model, which is a way to draw edges that allows for community structure. Now, for our baselines, we have three models. The first has oracle access to everybody's infection state. It's unattainable, but it tells us what is the best possible performance. The second baseline is a no exposure model, which completely ignores the exposure state and just attempts to make a prediction based on the susceptibility characteristics. And the final is the optimistic model, which takes into account the exposure, but it assumes that everybody who is untested is also uninfected. In the first set of experiments, we vary the testing odds, which is the probability of testing a sick individual divided by the probability of testing a healthy individual. On the left-hand side of the x-axis, we have randomized testing, and on the right-hand side, we have very biased testing, where symptomatic folks are far more likely to become tested. Now, the y-axis, we have the mean AURC on the held-out test set, and if we look at the performance, we see that our model outperformed baselines at almost every level of bias. And at the very high level of bias testing, we perform as well as the baseline. This happens because our model is able to impute good enough labels for the untested individuals, which effectively increases our sample size. In the second set of experiments, we vary the proportion of the population that is tested, and that's what's shown on the x-axis. Again, on the y-axis, we have the AURC. We see that our model outperforms all others on every level of testing, and at high enough testing levels, we get close to oracle accuracy. Now we can look at some of the real data experiments that we have. And in our real data task, we want to predict the onset of Clostridium difficile infections, or CDI infections, among patients at the Massachusetts General Hospital. We extract daily labels or daily labs, medications, procedures from the electronic health records, and we construct three different types of networks. The first is based on room sharing, the second is based on nurse sharing, and the last is based on either room or nurse sharing. Now here, we don't have access to the true labels like in the simulation, but we create a proxy label for asymptomatic carriers as follows. There are two types of tests that are used to identify CDI infections. The first is a toxin test, and if the results from the toxin test are inconclusive, another highly sensitive test called the PCR test is used. And there has been a lot of discussion in the medical literature pointing to the idea that patients who test positive using the PCR tests are milder and not incredibly symptomatic patients. So during training time, we hide the PCR positive patients from the algorithm, and we only allowed access to the toxin positive patients. And at test time, we compare the predicted label to the infection state regardless of whether or not it tested positive using PCR or toxin. Here we show the AURC on the test set, and we see that our model achieves the highest accuracy across all three contact networks. Somewhat surprisingly, the optimistic model does worse than the model that completely ignores exposure. This likely implies the hospital isolation protocols are effective because it implies that using only the infection states as a measure of exposure adds noise. Now, in summary, we proposed a model that predicts contagious infections in the presence of incomplete testing, and our model leverages both labeled and unlabeled data, hence outperforming the benchmarks on a real and simulated test setting. Thank you so much, and stay safe.
Hello, welcome to my talk on exploiting verified neural networks via floating point numeric error. I'm Kai from MIT CCL. Let's start with the neural network. If we give this test image from the CIFAR10 dataset, it will give us a prediction of airplane, which is correct. If we give it another image that looks the same as the first one, the prediction becomes a horse. This is called an adversarial example, which is a known vulnerability of the neural networks. Fortunately, we have neural network verifiers coming to our rescue. We can give the input image a perturbation bound, which is 2/255 in this case, and a neural network into a verifier. In this case, MIP verifier claims that all inputs within this 2/255 perturbation bound of this given image are classified as airplane, so we know that the network is verified to be robust with respect to this given input. Let's revisit the situation where these two images are classified differently by this verified neural network. MIP verify implies that the distance between these two images must be greater than the perturbation bound considered in the verification, which is 2/255. However, we have computed their distance, which turns out to be no more than the perturbation bound. So the only explanation is that the verification itself is wrong. To understand the reason, let's revisit the verification of real-valued networks. We have a mathematically defined neural network, which has real-valued weights, real-valued computation, and the network topology. We also have a robustness specification to be verified, which is the adversarial robustness against input perturbations in this case. They are converted into some formulation to be given to a complete verifier, which will give us an answer of whether this specification is guaranteed by this neural network. However, the inference computation of the network has to be carried out on some particular hardware with some inference algorithms. There is inevitable floating point error in both the inference implementation and the verifier. Different implementations really have different floating point error characteristics. The verifiers really do not try to exactly model the inference computation due to efficiency considerations. Therefore, the inexactness of modeling the inference floating point arithmetic allows us to construct adversarial examples for verified neural networks while exploiting floating point error. Here is our method. We start from a safe image whose perturbation space totally falls on one side of the decision boundary assumed by the verifier. The verifier therefore can claim that the network is robust with respect to this safe image. Starting from the safe image, we adjust its brightness to bring it closer to the decision boundary assumed by the verifier. And we call this image a quasi-safe image. Within the perturbation space of this quasi-safe image, we can find a quasi-adversarial image which is sufficiently close to the decision boundary assumed by the verifier. Due to the floating point error, there is a discrepancy between the decision boundaries of the implementation and the verifier. And it turns out that by randomly applying tiny perturbations on the quasi-adversarial image, it's very likely that we can obtain an adversarial image which falls on the other side of the decision boundary of the implementation, but it is still within the perturbation space of this quasi-safe image. We test our method on 5 implementations in the PyTorch framework for convolutional layers. They are either based on the CPU or GPU platform with a matrix multiplication formulation, a direct convolution formulation, or using the Winograd accelerated convolution algorithm. The verifier claims that the network is robust with respect to this airplane image. However, with our method, we can successfully find the images that fall within the perturbation space of this airplane image, but are classified as a horse on these 5 implementations. Our method also works for this horse versus deer image. We also test our method on the M-list dataset with a larger perturbation bound, and it also works. To be more specific, we test our method on 32 images, randomly selected from the verifiably safe test images of these 2 datasets. We can successfully find cross-adversarial images for 18 of them on M-list and 26 of them on CFR10. In this table, we show the number of adversarial images successfully constructed from the cross-adversarial images for each of these 5 implementations. The results indicate that our method can systematically exploit floating point error to construct adversarial images for verified neural networks. So what does this story tell us? Let's rethink the trade-off in verification. For an ideal verifier, we would like it to be complete, sound, and scalable. A complete verifier should be able to give a yes or no answer, possibly with a proof or counterexamples for each problem instance. It should never give an I don't know answer in any case. By soundness, we mean the verification result should always be correct. And a scalable verifier should be able to handle large neural networks relatively efficiently. We therefore face the trade-off between these 3 properties. If we are willing to accept incomplete verification results, we can work with the certification methods, which solve a relaxed form of the verification problem. Therefore, they are more scalable, but they are unable to give an answer in certain cases. If we want to be both scalable and complete when verifying real-valued neural networks, we may have to give up exact modeling of floating point arithmetic, which produces unsound results in certain cases, as we have demonstrated. Regarding this trade-off, I discuss 2 mitigation strategies. The first is to adopt over-approximation to incorporate floating point error in the verifier. For example, we can introduce error terms bounded by the maximum possible inference error into the formulation of the verification problem. However, it is unclear how much completeness or scalability will be lost by introducing such error terms. Moreover, it is very difficult to obtain a provable estimation of tight error bounds for a given implementation, especially for an optimized one on specialized hardware. Another strategy is to utilize network quantization. Quantized networks are more efficient in inference, and they don't have any numerical error issues. A prominent class of quantized neural networks are the binarized neural networks, which constrain their weights and activations to be binary. However, prior work of verification of binarized neural networks usually adopts an off-the-shelf set solver, which delivers slower verification compared to verification of real-value networks, which usually uses a MILP solver. And there is a lack of research on adversarial training of binarized neural networks, which leads to their robustness issues. Therefore, there is very little work that works with binarized neural networks in this field. Regarding this situation, we have conducted research on complete, sound, and scalable verification of binarized neural networks. We can successfully reduce the verification time by orders of magnitude compared to verification of real-valued neural networks. We also devised adversarial training algorithms for binarized neural networks, which delivers comparable robustness. Here are our contributions. If you have any questions, you are more than welcome to send me an email.
Hello, my name is Lucas Liebenwein, and I'm a PhD candidate with Daniela Roos at MIT CC. Today I'm going to present our work on Provable filter pruning for efficient neural networks. Now, as we all know by now, neural networks have achieved state-of-the-art performance on numerous tasks and applications like computer vision, robotics, and natural language processing. So one general trend that seems to have emerged is that actually networks with more parameters, so larger networks, in general perform better than their small counterparts. So a natural question that does arise is, can we take a large network with superior performance and turn it into a smaller network that still has the same performance but requires less parameters? Now, the advantages of a small network are straightforward. Smaller networks require less storage, you can do inference with them much faster, and they're potentially even easier to interpret because they might contain less features. Now, to this end, what we consider in this work is the problem of filter pruning. That is, we want to take a large network and we want to prune entire parameter groups from the network, such as filters and neurons in fully connected layers. More formally, what we're interested in is we want to find an algorithm and prove a certain property about it. Namely, we want to prove that we can find a dense reparameterization with less filters that approximates the original network up to 1 plus minus epsilon relative error. And we want this guarantee to hold with at least probability 1 minus delta. And finally, as I said earlier, what we want to have is we want this reparameterization to be much smaller than the original parameterization of the network. So now we split up this problem into two subproblems. The first subproblem being is like within a layer, we want to understand what is the relative importance of a filter. We term this the empirical sensitivity or relative importance of a filter. And so depending on your importance and then depending on your criterion, actually the filters you want to keep, which have the highest sensitivity, might change. The second question we're interested in answering is, now that we actually can prune within a layer, what is the optimal allocation of a budget across multiple layers? So in this case, we could ask ourselves, is it actually best to prune a fixed ratio in each layer, or might it be better actually to vary the ratio of what we want to prune in each layer? So maybe a more optimal architecture is what you can see now, where we chose a non-uniform budget allocation across layers. In terms of related work, there's been a lot of related work in terms of filter pruning. In terms of what people use as the sensitivity or the relative importance criterion, it varies, but it's mostly based on some kind of norm-based heuristic. And other approaches also, for example, consider some kind of greedy approach where you consider also the data. In terms of budget allocation, most other approaches either consider some kind of uniform budget allocation across layer or do some kind of manual hyperparameter tuning. And so the disadvantages of existing work is that we don't have performance guarantees, so we can't say anything about the theoretical properties of the pruning algorithm. And also from a practical standpoint, there's a lot of manual hyperparameter tuning involved that is very network specific and thus requires a lot of input from the practitioner. All right, let's dive into our method. So let's go to the first aspect of our method, which is like understanding the filter importance within a layer. Now the setup we consider is we have a fixed input x, that gets propagated through the layer, and then we arrive at layer L plus 1, it goes on to layer L, and so on. So now specifically what we're interested in, we are trying to understand layer L and the filters and neurons within layer L that actually get computed there. So what we want to do is, like for a given filter group WJL, and associated channel AGL, or in this case, how we visualize it as a neuron. You can essentially think of a neuron as a 1 pixel image, but the story or like the intuition remains the same. And so what you're trying to understand is how important is this neuron when you compare it to some of the other neurons within this layer, right? And so in order to do that, what we actually do is we kind of do like a look ahead. So we consider the next layer, right? And so in the next layer, what you can see is that our neuron here, AJL, actually contributes to a lot of the outgoing edges. So it kind of, contributes to all the other neurons in the next layer. And so what we want to more formally, what we quantify with filter importance is essentially what is the contribution that this particular weight has, right? So kind of like here, the weight and the neuron from this in layer L compared to the overall neuron. And so here, what we can see, for example, is like here for a particular neuron here, kind of that's the output term, right? And that neuron also gets a lot of inputs from the other neurons in the previous layer. And so here we kind of quantify the relative importance, so like the relative contribution of that particular neuron J in layer L. Now, as you can see, the neuron J, plays a role in multiple neurons. So actually we want to take a max so that we can consider the maximum contribution it has in this layer. Now, the second thing that I want to mention is that so far we've thought about a fixed input, but actually in practice what turns out what we can do is like we can compute that over multiple inputs and take the maximum as shown here. And what the maximum gives us that the sensitivity is well approximated for any of the input data points that we might expect coming from the same distribution. Now, equipped with this notion of filter importance, what is shown in the paper formally, is that we can obtain relative error guarantees for within layers, essentially by sampling proportionally to the sensitivity within each layer. And so once we decide to sample a neuron or we don't sample a neuron, right, then we can actually prune the incoming and outgoing edges from that neuron and effectively reduce the size of the network. All right, let's move on to our second problem, which is the idea of budget allocation. Now, as I mentioned in the previous slide, is that actually our error guarantees are of the form epsilon, which denotes the relative error, and this is a function of the number of samples you assign to that layer, right? So once you have that, you can imagine you can also compute the size for a given budget, whereas the size of the network is just a function of the architecture, like shown here. And now we actually formulate an optimal allocation problem where we say we want to minimize the maximum epsilon across all layers, given that we want to satisfy a certain budget. So this is very nice, and actually it turns out we can efficiently solve this via line search, like a binary search. And then it gives us an optimal allocation across multiple layers of how we want to allocate a given budget. All right, let's talk a little more about the theory as well. So using our relative error guarantees, we can also derive compression bounds of the form as shown here. So essentially we have this 1 plus minus epsilon relative error. We can make this hold with high probability, so probability at least 1 minus delta, and epsilon delta are a user specified constants. And so essentially now we can bound the number of filters by the quantity shown here. And so I want to point out a couple of terms in here. So there's epsilon squared, which is the relative error, and there's log 1 over delta, which is essentially the union bound that we require in order to make it work. So these are very standard terms for like sub-Gaussian concentration bounds. A few other terms that appear here is like this L squared. So we kind of have to scale down our error within a layer because now we have like L layers. So it kind of makes sense that this notion appears as well. Now the other two quantities that I want to mention is like, first of all, sum of sensitivities, as shown here. And sum of sensitivities is just the sum of sensitivities within a layer. And this kind of quantifies the spread of importance within a layer. So if you only have a few parameters that are important, sum of sensitivities is going to be low. And accordingly, in our bounds, we can see that we don't need to sample as much, and it's easier to prune and to approximate the layer with less samples. On the other hand, if the importance is spread out, sum of sensitivities is going to be large, and so it'll be harder to actually prune that layer, right? And so that's kind of quantified with this sum of sensitivity term. The second term I want to quickly mention is just this propagation complexity. So we also kind of have to do like we have to understand how the error propagates through the layer. So we kind of incur epsilon error within each layer. And so we have the L squared, which quantifies that, but we need an additional term to kind of keep the error low. Our analysis is kind of like worst case, so that's definitely something we're interested in working on in the future. All right, let's move on to some results. Here we show some prune-only results on ImageNet, and we can see that our theoretical guarantees nicely translate into practice, and we can outperform competing state-of-the-art heuristics. Here are also some interesting results in terms of the budget allocation. So here we pruned the VGG and we plotted the budget allocation per layer compared to like a uniform budget allocation. And what you can see here in early layers, we actually oversample. And that makes sense because in the early layers we have relatively small filters, relatively large images, so there's a lot to like approximate, and so it makes sense that we need to keep more parameters. Here, kind of like in the middle region, what happens is actually we kind of undersample, and the reason for that is in the middle layers they kind of more look like fully connected layers, so there's a lot of parameters. And obviously the last layer, quickly mentioned, we want to sample a lot from that because that's the layer that's responsible for classification. All right, moving on. We also considered, incorporating our pruning strategy into a more classic prune pipeline where we basically train, we then prune filters from the network, and then we retrain the network and we iteratively repeat that multiple times until we hit the desired prune ratio. So also in this case, and it's nice to see, although we didn't explicitly consider retraining in our analysis, that we can also compete with other state-of-the-art heuristics that were specifically built for those kind of retraining pipelines, and we actually outperform them even and get even higher, more highly compressed networks. Okay, with this in mind, I would like to conclude. Feel free to email us and contact us if you have any questions. Paper and code is available online, and I thank you for your attention.